Hello everyone, welcome to this video where I will explain the two concepts. The one is Euler's theorem, what is this Euler's theorem is and what is the use of this Euler's theorem, and the second part is testing for the primality. That means we have to check whether the given number is prime or not. So by using something called as a Miller Rabin's algorithm, let us find whether the given number is prime or not. Okay, now let us start with the first part of this video, that is Euler's theorem. Okay, now this Euler's theorem is nothing but it is the generalization of the Fermat's theorem. Okay, the Fermat's theorem says a to the power p, the prime number, is congruent to 1 mod of n. Now in this case, in the Euler's theorem, is simplified, it is modified here. We have taken a to the power phi of n, where this phi of n is the torsion function of any integer n. It can be a prime number, it may not be a prime number. If it is a prime number, then in that case, this Euler's theorem is same as the Fermat's theorem, you can say, right? But n can be any integer. It can be a non-prime number also. Okay. Then you find the torsion function of this. Okay, that is phi of n. And if it is congruent to 1 mod n, it is always congruent to 1 mod n. That is, a to the power phi of n mod n is always equal to 1. The reminder, it is equal to 1 always, where this a and n is actually co-prime numbers. That is, GCD of a and n is equal to 1. Okay, so if the n is a prime number, in that case, as we have you know that already, that the torsion function is nothing but it is n minus 1 in this case. Okay, now how to prove this particular theorem? Okay, what we have to prove here is we have to prove that a to the power phi of n is congruent to 1 mod of n. Okay, this is what I have to prove. Now I start with a few equations and I'll explain that with an example also, because without example it is very difficult to understand the equations. Now I'll go with the equation first of all. Okay, now what is this phi of n? The phi of n is nothing but it is the number of positive integers which is less than n, but which are co-prime to n or relatively prime to the given number n. Okay, that is the torsion function. Now let us consider such co-prime numbers as R, the set R. Okay, the set R actually represents all the co-prime numbers for n. Okay, if I take an example of say 5, the co-prime numbers are maybe 2 and 4, right? These are the co-prime numbers. So only 2 numbers will be there, right? Or for example, let us say a is equal to 3 and n equal to 10. So n is equal to 10 in this case I have taken. What are the co-prime numbers to this? The co-prime numbers are, okay, the torsion function is 4, okay, and the co-prime numbers, relatively prime numbers, are 1, 3, 7, 9, because 1 GCD of the 1 and 10 is 1, 3 and 10 is 1, 7 and 10 is 1, 9 and 10 is 1, right? So in this way I have listed all the elements of R which are nothing but they are the positive integers which is less than n, but they are relatively prime to the given number n. Now what is this a is, I'll tell you. Now what I'll do is I'll multiply to prove this particular theorem, that is Euler's theorem. I'll multiply all the elements like x1, x2, x phi n, that is 1, 3, 7, 9 in my example, by the number a. Okay, I'll take a number a which is less than n in this case. I'll multiply that with these elements here, elements of the set S. Now what I'll get by mathematically, I'll take it as S, which is equal to a into x1 mod of n, a into x2 mod of n. So I multiplied x1, x2, x3, maybe x phi of n by a. Okay. Now if I reduce that by again mod n, what I'll get is it is nothing but this R and S. The elements of both the sets are actually same. Okay. I multiplied by a, all the elements of this are multiplied by a, and I reduced it by n in this case, right? So this set S is nothing but it is set R, but it is not exactly set R, but the elements are same, but it is a permutation of R. Let's just look at this example. Just look at this. So this is what I have done. So I have got a S here by multiplying with a, that is 10, reduced by n. Okay, multiplied by 3, I'm sorry, and reduced it by 10. So what I'm getting here, I'm getting 3917, which is nothing but the permutation of R itself, right? So I considered these two equations. Now, so that's what I have told just now, the permutation of R, right, with following reason. Now what is the reason? Because a is relatively prime to n, that is 3 is relatively prime to 10 here, Okay, xi is also relatively prime to n. So what is this xi? 1, 3, 7, 9. So all these 4 elements are also relatively prime to 10 in this case. That means a into xi must also be relatively prime to n. That is, a into xi means 3 into 1, that is 3, 3 into 3, that is 9, 3 into 7, that is 21, 3 into 9, that is 27. All are relatively prime to n. So this is the one reason. Okay, that's why we get a permutation over there. Okay, and there are no duplicates. There are no duplicates in the set S. 3, 9, 1, 7 are the individual numbers, same numbers but with a different permutation I am getting here, right? That means if AXI mod n is AXJ mod n, if that is the case, that means XI should be equal to XJ. Fine. Now, using this, now what I will do is, I consider this again R and S, okay? I will multiply all the elements of this, I will multiply all the elements of this, okay? And I will multiply all the elements of this. The answer should be same, right? Isn't it? I reduce it by n again. Just look at this. The product of a into xi mod n, okay? And which is actually equal to the product of xi. That is the previous slide here. Because since the elements are same, if I take a product of this 3 into 9 into 1 into 7, 1 into 3 into 7 into 9, I should get same answer, correct? It is equal. So that's what I have written. Fine. So that means in the form of a congruence operator, if I write it, it is a product of all the elements of that set. Phi n number of elements are there. A into xi is congruent to xi, product of all the elements, that is xi mod of n. So that's what I'll get. Now, see here I have a as a common term, and I have actually phi n number of a's, right? I'll split it, this particular term, into 2 separate parts. How to do that? Just look at this. Okay, it is, I have a repeated, this a is repeated phi n number of times, correct? So I have taken that outside, and the remaining term I have written as it is here, that is product of xi terms, and such a phi n elements are there, which is congruent to the same thing here, right? So in this case, what we can do is we can cancel out this and this. Just one second. Yeah. So this and this I can cancel out. Okay. So this comes out to be 1 here. That is 8 of phi of n is actually equal to 1 congruent to, I'm sorry, 1 mod of n. Okay. This actually proves the Euler's theorem. So this is the Euler's theorem says what? A of phi of a to the power phi of n is congruent to 1 mod n. So I have proved it by using these equations. Okay. Now, few examples. Let us go with say a equal to 3 and n equal to 10, which is my previous example. And we know that phi of 10 is actually equal to 4, and we know the elements also, that 1, 3, 7, 9 are the elements. So a to the power phi of n, that is 3 to the power 4, is nothing but it is 81. It is congruent to 1 mod 10, right? That is 81 divided by 10, which gives you the remainder, okay, the modulus, okay. The modulus is actually equal to, remainder is actually equal to 1 in that case, right? That's what I'll get this answer. So this condition is holds true. Now if I take a equal to 2 and n equal to 11, okay, phi of 11 is a prime number, but phi of 11 is 11 minus 1, that is 10, that is 2 to the power 10 is 1024, is actually congruent to 1 mod 11, because again 1024 mod 11 is actually equal to 1. Okay, so this proves the Euler's theorem. Okay, and this is another way of representing the Euler's theorem. That is, a to the power phi of n plus 1 is actually congruent to a mod of n. Okay, it's a congruent, actually it's not equal operator, it's a congruent operator. So I have to put one more line here. This is a congruent operator. Okay, so this is another way of saying that is a to the power phi of n plus 1 congruent to a mod of n. Okay, so where a and n need not be necessarily relatively prime number. Okay, this is a generalized version of the Fermat's theorem. Now, this is the second part where we are finding the, or we can say, I have a given number, maybe a very large number. We have to verify whether this number is prime or not. Okay, so we have an algorithm given by Miller Rabin. Okay, so we will use this algorithm to find or to identify the given number is prime or not. Okay, but before going into that particular algorithm, few preliminaries we will understand here. That is, one is the two properties of the prime numbers. But before that, just look at this equation. Now I have a let us say odd integer, which is n. Let us consider, which is very much the larger number, which is more than or equal to 3. Let us consider. Okay, this can be represented in this fashion. That is, n more than or equal to 3, any number which is more than or equal to 3 can be represented as n minus 1 is always equal to 2 power k into q, where this is any integer, k is any integer which is more than 0, and q is always an odd integer. Okay. For example, just look at this. I have a n equal to 9, first example. Second example is n equal to 23. How to represent this 9? 9 minus 1 is 8, right? That is 2 power 3 into 1, correct? Just look at this. So 8 can be represented as 2 power 3 into 1, where this 3 is k and 1 is an odd number. What about 23? 23 minus 1 is 22. That is, just look at this. 2 power 1 into 11. 11 is an odd integer always, right? 2 power 1 is a k. Value of k is 1 in this case. So this is any odd integer can be represented in this fashion. So I need this representation when I go to the Miller Rabin algorithm. Now, as I told earlier, so we have two properties of the prime numbers. We have to understand those properties, and we have to, in the Miller Rabin algorithm, we have to verify any one of the property. If one of the properties satisfies, then we can say that the given number is a prime number. Okay. Now, what the first property says? The first property says if p is a prime and a is some positive integer which is less than p, okay, then a square mod p is always equal to 1 if and only if a mod p is 1 or a mod p is minus 1. Okay, minus 1 means it is p minus 1, right? If I reduce it by again a p, I'll get it as p minus 1. Okay, so if p is a prime number and a is some positive integer, if I consider any integer, let us say, which is less than p, the prime number, then a square mod p is equal to 1 if and only if a mod p is either equal to plus 1 or is equal to minus 1. Minus 1 means it is converting into positive number, it becomes p minus 1. Okay, so that's what I have mentioned over here. If a square mod p is equal to 1, then a mod p whole square is also equal to 1, which is true only when the case a mod p is 1 or a mod p is p minus 1 or minus 1. So this is the first property. Now what about the second property? The second property says, let us consider p is a prime number which is greater than 2. Okay, then in that case we can represent in this fashion. This is what I have told earlier, right, in the previous slide. But here I am specific that p is a prime number. It is not necessary that p is any integer, but p is a prime number I have taken. Okay, so p minus 1 is equal to 2 power k into q, where q is some odd integer. Okay, and k is more than 0. Okay, now and we can choose that a that we consider that a which is between 1 to p minus 1. Okay, now in that case either this condition is true, okay, or the condition 2 should be true. If a p is a prime number, either we have to prove that this condition is true or the second condition is true. Now what is this condition is? The condition is a to the power q for any value of the a which is less than p minus 1 to the power q, which we find over here, okay, congruence to 1 mod p. It should be, okay. Or the second, if this is not true, in that case, okay, either a to the power q or a to the power q square, which can be written as a to the power 2q, or a to the power 4q square of the previous number, okay, or so on, a to the power 2 to the power k minus 1 into q is congruent to minus 1 modulo p or p minus 1. That's what I have given here, right? So for any value of say j which is between 1 to k, okay, what the value we find here k, the value of the j is more than or equal to 1 or less than or equal to k, between 1 and k, we can say if this condition satisfies, then I can say that the given number is a prime number. Okay, that is a to the power 2 power j minus 1 into q congruence to minus 1 mod p, which is equal to p minus 1. So I have to prove either this. If this is not the case, then I have to check for this. If this is equal to p minus 1, okay, in that case I can say that, I can conclude that the given number is a prime number. Now let us understand this with the proof, and finally with the example. Okay, so we have to prove that p is a prime number. Just one second. Yeah, p is a prime number. Either the condition 1 or the 2 should be satisfied, as I told earlier, right? So p minus 1 is 2 power k into q. That's what I have written here. And from the Fermat's theorem, little theorem, we know that a to the power p minus 1 congruence to 1 mod of p, right? A to the power p minus 1 is congruence to 1 mod p. Now what is this p minus 1 is? I substitute that p minus 1 by 2 power k into q. So it should be the case that a to the power p minus 1 mod p is equal to a to the power 2 power k into q mod p. So I have substituted that p minus 1 as 2 power k into q, right? isn't it? Is equal to 1. So from the Fermat's theorem, we know that this a to the power 2 power k into q mod p is always equal to 1. We have verified that. We know that, right? So we can represent something like this. That's what I have mentioned here. Okay. So let us restrict the value of the a to be less than p minus 1 only in this case, to stick with that Fermat's concept, Fermat's theorem. Okay. And let us understand now. Let's look at this. I'll choose some number, okay, some integer, let us say a, in the range of this p minus 1. It can be anything. Okay, I'll take up an example and I'll explain again later these concepts. We will verify this. This is the first condition, right? A to the power q mod p should be equal to 1. Or else, a to the power 2q mod p, a to the power 2 square q mod p, a to the power 2 cube q into mod p, and so on, a to the power 2k into q mod p should be equal to 1 or minus 1. It should be. In that case, that p, this is the prime number. Okay? So, each number in this series are nothing but it is the square of the previous number. So this number is square of the previous number. This number is square of the previous number. Okay. Therefore, one of the possibility out of these two should be true. That's what I have told now. First number on the list and therefore all the subsequent numbers on the list should be equal to 1. If this is equal to 1, the square of all these numbers will be equal to 1. Right. Some number on the list does not equal to 1. So this number may not be equal to 1. This number may not be equal to 1. But the square of the previous number may be equal to 1. Okay. And that number is nothing but it is always p minus 1 if p is a prime number. Now, let us understand this by using the example. Okay. Now, this is the algorithm, Miller's Rabin algorithm steps. We will apply those conditions to this particular test and we let us verify, okay, whether the given number is prime or not. So, I have taken a number n. Okay. So, this is my algorithm. This is my algorithm. Fine. So, test of n is a function which I have written. We have to find the integers for a given number n. We have to find the integers, like say k, q, okay, where q is an odd number, using this particular formula. That is n minus 1 is equal to 2 power k into q. This is the first step. Fine. After finding those k's, q's and all, what we have to do? We have to select particular random number, say a. I have to choose one random number here, a, which is in the range of 1 to n minus 1. Any number, it can be any number. See, if I say n is equal to 11, okay, 1 to 10, any number we can choose. Okay, and we have to work with more number of a's. Remember, I'll tell you about that. Now, if this is the first condition, right? I'm verifying the first condition, that is a to the power q mod n is equal to 1. If this is equal to 1, I'll verify this, I'll calculate this, I'll verify this. If this is equal to 1, my test will send the result as inconclusive, because by using single 1a out in the range of say 1 to n minus 1, we cannot decide whether the given number is prime or not. So always my test result is inconclusive if the number is prime. If this is not the condition, if this condition doesn't holds good, I have to go check the second condition, right? So with the values of j equal to 0 to k minus 1, what we have to do? We have to do these things. That is a to the power, just one second. Yeah, a to the power 2 power j into q mod n should be equal to n minus 1, or it is minus 1. If this is the case, then again you send the result as inconclusive only, because I say you have to verify for more number of a's. Okay. Now, if this is not the case, if both the conditions are not true, this condition and this conditions are not true, then the given number is not a prime number, but it is a composite number. Now, just look at this. I have an example. My example is n equal to 29. As you know, 29 is a prime number, right? Let us verify that by using the Miller's Rabin algorithm. So, what is the first step? According to my algorithm, the first step is n minus 1, that is 28, I need to represent in this fashion. That is 2 power square into 7, which gives me 28, right? Where k is 2 and q is 7. So what we have to do first, we have to verify the first condition, that is a to the power. I'll try with some number, say random number a equal to 10, which is less than 29. So I can have a 28 numbers, 1 to 28. I can choose any number there. Randomly, I have picked a equal to 10. So what we have to calculate, a to the power q mod n, right? That is 10 to the power 7 mod of 29, which gives me 17. Okay, which is neither 1 nor 28. That is either minus, it's not plus 1 or minus 1. So I'll continue my test. I cannot say it is composite number, but I'll continue that with the another second condition. So I checked only a to the power q mod of n, right? Now I'll go to a to the power that is 10 to the power 7 square, that is 7 into 2, that is 10 to the power 14 mod 29. So what I'm getting 28, that is n minus 1, right? So my test will return it as inconclusive. It may be a prime number. Now just verify. I'll take up another number here, that is a equal to 2. Okay, because I said 1 to 28, I can choose any number. If you choose all the numbers, then it is fine. You verify the output, check whether it returns no, inconclusive most of the time. Okay, let us try check with this a equal to 2. So first I can try with the a to the power q mod of 29, which gives me 12. No, I cannot decide here. I'll go with the second case, that is a to the power, that is 2 to the power 7 into 2, right? I'll go with that. I'll get a 28 again. Just look at this. I get a 28, that is p minus 1 or n minus 1, right? It returns the inconclusive. So you verify with most of the numbers, 1 to 28, it will return it as inconclusive. So that means the given number is a prime number in this case. Okay. So two important steps. This is the first step. This is the second step here. I have ended with the second step because my k is equal to 2. So only two values, two calculations. That's it. Now just look at this example. Miller's Rabin algorithm. So the second example, my number is composite number. 13 into 17. Both numbers are actually prime numbers, 13 and 17, but their multiplication is 221. May not be a prime number, right? It's a composite number. Now let us verify this. I'll start with again this first step. N minus 1 is 220, 2 power 2, 55. Again k equal to 2. Two calculations I need to do, and q equal to 55, right? I'll start with a equal to 5. So my n is 221. I can choose any number between 1 to 220. Let us choose the number as 5. So the first calculation, a to the power q mod of 221, which gives me 112, which is neither 1 nor 220. I'll go with the second step. 5 to the power 55 square, that is 5 into 55 into 2, which gives me 168. No, right? Both the time it is not 1 or 220. I'll choose a different number now. So my number, okay, in this case I tried with both the numbers. It is definitely a composite number, I can say, with one value of a. Okay, this one value I have selected here, a equal to 5. Now just look at this. I have selected value a equal to 21. Okay, so I have to calculate 21 to the power 55 mod of 221. What is the answer? The answer is 200. Okay, the answer is 200. No, I'll go with the second case. 21 to the power 2 into 2, 55 mod 21. I'm getting 220. 220. See this. It is n minus 1, right? So my test returns inconclusive in this case, saying that 221 may be a prime number. Okay, if I verify with say a few numbers, let us say all the 218 integers from 2 to say 219, 4 of these numbers like 21, which I have selected here, 47, 174 and 200 will return the number as prime number here, even though 221 is not a prime number, right? So that means there is a possibility that my algorithm, Miller's Rabin algorithm, may give you the wrong result. There is a possibility. What is the probability? Let us understand this now. Okay, this is the probabilistic consideration. Now, so Miller Rabin algorithm returns a composite, the number is definitely not a prime number. If it results, say, sends a composite, definitely it is not a prime number. Okay. Now, there is a possibility of sending a wrong signal, right, or wrong information. Correct? What is that wrong information you can send? Chances that it detects the pseudo prime, that is, it will fail to detect that n is a prime, n is not a prime, is less than 1 by 4. Okay, that's 20. You can say 25%, right? Thus, if I conduct say 20 number of tests, okay, I conduct t number of tests actually with the different values of a. T can be a huge number, it can be a big number. Okay, that means I choose different values of a. In that case, the probability that all of them will pass the test or returns inconclusive for n is less than 1 by 4 to the power t. Okay, for example, let us say t equal to 10. The probability that a non-prime number will pass all the 10 tests is just less than 10 to the power minus 6. Okay, a non-prime number saying that it is a prime number. Okay, if I go with the t equal to 10, that probability will reduce to 10 to the power minus 6. That means for large values of test, okay, repeatedly considering different values of a, okay, the probability will go down. The probability of wrong information will go down. Okay, so we have to go with the large numbers basically. Fine. So in this video, I have explained what is this Euler's theorem is. Okay, the totient values, a to the power pi of n is congruent to 1 mod n, right? And the second part, I have explained how to find or how to test whether a given number is prime or not by using Miller's Rabin algorithm. Thank you for watching this video.